Topic 2.2 Crystal Structures of Metals. In the last topic, we have seen how the storm structure affects the metal properties. And now, in this topic, we will go a little deeper in the crystal lattice of the metals and see how it will influence plastic deformation of metals. So the crystal structure of metal is made up of the repetitive translation of the unit cells piling up into a 3D structure. And if you look at this picture, it looks like a box or a cube. It is the unit cell or lattice point. And the atoms occupy different locations in the space of the lattice, as you can see from this picture. And if you think of these unit cells piling up in a 3D structure, imagine like you were playing building blocks when you were young or put on the Legos to make the 3D structure. So we have the crystal lattice structure like this. Therefore, the crystal lattice is the arrangement of atoms or groups of atoms in a crystal. So now let's have a look at a little further on the unit cell, as you can see from this picture showing the geometry of crystal lattice. The unit cell is referred to the principal axis X, Y, and Z, as you can see here, X, Y, and Z. There are 6 lattice parameters. The first 3 are on the lengths along the cell edges, which are A, B, and C. All the 3 are the angle between them. Here the alpha, beta, and gamma. And for the cubic structure, like this, A and B and C are equal. And hence, alpha, beta, and gamma are 90 degrees or normal to each other. Let's have a bit of calculation of the lattice parameter. Giving you here a piece of metal, for example, is the iron, having a 1 centimeter long. And the question is, how many unit cells of iron in a 1 centimeter long? I've given you the lattice parameter for iron is 0.287 nanometer. And I introduce you again the cubic structure having its length of 0.287 nanometer. So we have to find out how many of these gonna be lying along this 1 centimeter long. First, we have to change the unit from the centimeter here to meter, and also from here nanometer to meter as well. Then start the calculation. Above here is the 1 centimeter long, which is 1 times 10 to the minus 2 meter, divided by the lattice parameter, which is 0.287 times 10 to the minus 9 meter. Here it comes, the result is 3.48 times 10 to the 7. That's a huge number. And then if we change this number into millions, we then end up with there are 34.8 million unit cells of iron in a 1 centimeter long. There's a huge number there, isn't it? Actually, for polycrystalline materials like light metals and ceramics, there are various crystal structures, for example, bodycenter cubic, face-center cubic, hexagonal close-packed, tetragonal, rhombohedral, triclinic, and monoclinic, for example. But for metal, as we will emphasize in this class, I will give you 3 important crystal structures, namely body-center cubic or BCC, face-center cubic or FCC, and hexagonal close-packed or HCP. And the name has its meaning too. So these are the crystal structures of BCC, FCC, and HCP. So let's get on the detail. First, on the BCC structure, seen here is a cube lying on the reference axis, which are X, Y, and Z. Here we have the atoms sitting at the corner. 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 atoms at the corners. And here, one in the center, hence the name for the center cubic. And what I highlight here is the plane that contains the most atom. And this plane will move easier than other planes. And I will come back to this later. And let's move on to first center cubic or FCC. I introduced you here again is a cube on X, Y, and Z axis. And then we have 8 atoms on 8 corners. Now let's consider the faces of the cube. How many faces of the cube? Right, there are 6 faces. Now we have the atoms lying on 6 faces. 1, 2, 3, 4, 5, and 6. And here comes the face center cubic, or FCC. Now let's move on to the last one, hexagonal closed packed. We have here the hexagonal prism having 3 axes along the horizontal, namely A1, A2, and one in the opposite direction here is the A3. Another direction here on the vertical line is the Z-axis. Now I introduced you 6 atoms sitting on 6 corners on the top basal plane. And another basal plane down here also have 6 atoms sitting on 6 corners. On each basal plane, we have 1 in the center. And in the hexagonal prism, we have 3 atoms inside. Now we can see that we have total atoms of 2 atoms for BCC, 4 atoms for FCC, and 2 atoms for HCP. And I will come back to these numbers later in details. And for example of the metals having BCC structure, first, the ferrite iron, chromium, molybdenum, and tungsten. And for FCC metals, they are aluminium, copper, lead, gold, and nickel. And lastly, for HCP, the examples are alpha titanium, zinc, magnesium, and cadmium. And now let's count the number of atoms for each structure. And from the last slide, we've seen that the FCC structure having 8 atoms at corner and 6 atoms on 6 faces. What I'm going to do now, I would like you to exclude the space outside the cube and just consider within the cube only. And we can see that from this model showing the atoms that lying just within the cube. Each corner, there's just 1/8 atom sitting on. So therefore, we have 1/8 atom at 8 corners over here. And let's look more on the face. Just half of the atom lying on the face. And hence, just half an atom on 6 faces. Here come just 3 atoms on the faces. Now we have 1 atom on the corners and 3 atoms on the faces. We come up with the number 4 atoms per unit cell for FCC crystal structure. And if you see this picture showing the stacking sequence of the FCC structure, imagine we have this gray layer of atoms, and I give the name layer A. And then we have B layer of atoms stacking on A, and C stacking on B. The stacking sequence for FCC structure is then A, B, C, and repeating all along A, B, C, A, B, C. And this will give you the closely packed structure in 3D, as you can see from the picture on your right-hand side. Now I insert a box here, and you will recognize the corner atoms and the face atom over here, and lying here on the triangle showing you the most densely packed plane that we were talking about this in topic 2.3. Now for the atom that's closely packed, it's important to see how much space in the cube is occupied by the atoms, and it will relate to plastic deformation of the metal itself. Here's the parameters. Is the atomic packing factor, or APF. APF can be calculated as the ratio of total sphere volume, or Vs, divided by total unit cell volume, or Vc. And the definition of the atomic packing factors is the fraction of solid sphere volume in a unit cell. And I give you back here again is the 3D model of the FCC structure showing the atoms within the cube. And with this cube, an A is the lattice parameter showing the length of the cube. So therefore we have the volume of the cube, or the Vc, equals A cube. And if we consider that the atom has the radius r, therefore along this diagonal length that will equal 4r. Now let's consider this triangle. We will come up with the relation here, a squared plus a squared equal 4r squared. Hence we have a equals 2 square root 2r. As we already have that the unit cell volume of Vc equals a cubed, and then we replace a with 2 square root 2r over here. Then we come up with 16 square root r cubed, and here we have the total unit cells volume of Vc. Now we have to find Vs to calculate APF at the end. So do you remember how many atoms occupying in the space within the cube of FCC structure? There are 4 atoms inside. Next, you have to recall the volumes of the sphere. Right, we have here the volume of the sphere is 4 over 3 pi r cubed. Since we have 4 atoms, then we have the total sphere volume as 16 over 3 pi r cubed. Now finally, we can calculate the atomic packing factors, which is the Vs over Vc. Then we come up with the number 0.74. It means that 74% of the space within the cube is occupied by the, and that's quite high. And we can say that for the FCC structure, it's densely packed. And now let's have a look on the BCC structure and see how many atoms lying within the cube. I introduced you here again 8 atoms on 8 corners. And for BCC structure, there's 1 atom in the middle. And therefore, in the same case, we have 1 over 8 atom at 8 corners. Hence, we have just 1 atom. And 1 atom here in the center. So overall, we have 2 atoms per unit cell for BCC structure. And picture on the right-hand side here showing you a 3D models of the BCC structure. I now again insert with a box here. And you can see that these are the corner atoms, and 1 here in the middle for center atom. And the last one, hexagonal close-packed crystal structure. Remember that we have 6 atoms lying on the basal plane at 6 corners. 1 above here and another basal plane here. We also have 6 atoms at 6 corners on the bottom basal plane. And here there's 1 atom on the center of each basal plane and 3 atoms within the hexagonal prism. And let's have a look on this 3D model. And you can see that 3 atoms are inside the hexagonal close packed, and half of the atom on 2 faces of the basal planes. And here we have just 1 over 6 atoms on 12 corners of the basal planes. And here we have 6 atoms for the whole hexagonal prism. But for HCP crystal structure, it's not a cubic structure, and the unit cell is considered as the green prism here, which is just 1/3 of the volume of the whole hexagonal prism. And therefore, the actual atoms per unit cell will come down to 2 atoms per unit cell in this case. Now, if you have a look on the picture on right-hand side, in the case of HCP structure, Layer A is down here, and on the top here we have layer B, and then the stacking sequence will repeat from A, B, A, B, A, B. And if now I insert the hexagonal here, then you will recognize the basal plane here, 1 atom at the center and 6 atoms at the corners. Now this slide summarizes the lattice parameters of BCC, FCC, and HCP structured metals. First on the BCC metals, giving you a range of metals such as chromium, iron, molybdenum, and so on, with its lattice constant and atomic radius. And then the FCC metal, including aluminium, copper, gold, lead, nickel, platinum, and silver. And last one for the HCP metal, having two lattice constants, which are A and C. And normally in this case, we also have C over A ratio. So you can see that there are huge details in here. But I would like you to concentrate on particular metals, such as iron for BCC, and aluminium, copper, and nickel for FCC metal. And for HCP metal, let's concentrate on magnesium, titanium, or even zinc. And now you can see that the lattice constant is ranging from 0.28 or up to 0.4 in this case. Another important lattice parameter is atomic radius. This slide shows the periodic table of the elements and giving you the relative atomic radius. And you can see that the atomic radius increasing towards the left-hand side of this periodic table and down the table. And the radius of the atoms are quite important for making metals into alloy. For example, if we put nickel into copper, then we make the alloy called cupronickel that contains 10 to 30% of nickel. And this will give specific properties to the alloy, having good corrosion resistance and strength. So, the cupronickel is normally used for heat exchanger for engineering applications. It means that if the size of atoms are not much different, it is easy to be alloyed, and that can be used to a variety of applications. Now let's move on to another lattice parameter, which is coordination number or ligancy. The definition of coordination number is the number of atoms surrounding the central atom. I'll give you the example of the coordination number in simple cubic structure, as you can see from this picture, that we have the cubes in 3D structure and the atoms lying on each corner. And for the definition, we have to find the number of atoms surrounding the central atom. Then first we have to locate the central atom, which is the red one here. Now let's count the number of atoms surrounding it. 1, 2, 3, 4, 5, and 6. So the coordination number in the case of simple cubic structure is 6 atoms. And now let's check on the FCC crystal structures. In the cube here, we have 8 atoms at 8 corners and 6 atoms on the face. What we have to do now is to locate the central atom, which is the red one here. Now let's count the atoms surrounding it. 1, 2, 3, 4 from the top layer, and 5, 6, 7, 8 from the middle layer, and finally 9, 10, 11, 12 from the bottom layers. So here we come. We have 12 coordination number for FCC crystal structure. Now this table summarizes the lattice parameters once again for BCC, FCC, and HCP structure metal in terms of coordination number, number of atoms per unit cell, and atomic packing factor, or the percent of space occupied by the atom in the unit cell of the BCC, FCC, and HCP crystal structures. Now first let's consider the FCC structure. We have 12 coordination number with 4 atoms per unit cell, and this will occupy 74% of the space within the cube. And for HCP crystal structure, we also have 12 coordination number, as is also closely packed structure as well, with 2 atoms per unit cell that will give 24% of the space occupied by the atoms in the unit cell. And the last one is the BCC crystal structure, having 8 coordination number with 2 atoms per unit cell, and that the atom will occupy just 68% of the space within the cube. And what I would like to highlight here is the atomic packing factor. The higher number shows that the structures are closely packed, and that will influence the mechanical property, the deformation of the metals when we do the working operations. But I will give you more details in the next topic.